Hello, this is chapter 1 from Essentials of Radiographic Physics and Imaging, the 3rd edition. This first chapter is probably got a lot of information that is somewhat of a review from things that we've already learned in our other class, but there might be potentially some new information that you might not be aware of, or we might add a little bit to what we already know. So I hope you have printed the PowerPoint and you're ready to take some notes, because some of the information that I give you won't necessarily be on the slide, but will be in lecture. So let's start off with chapter 1, and this actually begins in your book on page 1. And this whole thing is just kind of like an overview and an introduction to the imaging sciences. This is a picture of Dr. Wilhelm Conrad Röntgen. He was actually born in Germany in 1845. He got his PhD from the University of Zurich, and he went on to become a professor, a mathematics professor and a physics professor. But he ended up being named a director at the newly formed Physics Institute at the University of Würzburg in 1894. And in that university, he and his wife actually lived at the university. They had an apartment up on the top floor, and he actually had a laboratory that was I take that back. His home was on the bottom floor, and he had his laboratory was up at the top of that building. And they also had their adopted daughter. It actually was his wife's niece that they adopted, so they had no biological children, but they all lived in the University of Würzburg. His wife was named Josephine Bertha Ludwig. He referred to her as Little Joe, and the three of them lived there. But it was in that laboratory that he changed the world of medicine as we know it. As far as his discovery, the details are not super specific. We've talked about this before, that upon his death, he did request in his last will and testament that all of his lab notes and books and anything that he had about his discovery, he requested that they be destroyed unread. So because of that, it's really hard to establish a detailed account of exactly what happened during his discovery. The only thing they can go by there were roughly 3 authors that interviewed him about his discovery. So between their papers and the 3 papers that he himself wrote about the discovery, that's pretty much where they get all of his information from. On Friday, November 8th, 1895, Dr. Röntgen was actually working in his lab, and he had prepared a series of experiments involving what was called a cathode ray tube. In his laboratory, somewhere close by, some reference it was over in a corner, some say that it was in an open desk drawer, but there was a piece of cardboard that was coated with barium platinocyanide, and each time he energized the tube or provided electricity to that tube, the screen glowed. He noticed that glow every time the tube was energized, and he had actually gone on to cover the tube with black cardboard so that he could actually do his night experiments. And he knew that the visible light that he was seeing from the cardboard couldn't have been from the tube, because he covered it and he was sure that no light was escaping. So he was just consumed with trying to figure out what it was that was causing that screen to glow. So because of that, he stopped what he was working on and started investigating the phenomenon. And he literally spent the next 7 weeks investigating that. He discovered in those 7 weeks nearly every single property of x-rays. He listed 12 in his original paper, and I can tell you that to date, no one has taken away from those 12 properties, nor has anyone added anything to those properties. Sometimes when you see the properties listed, they'll group some together, so they only list 10, but Rankin actually had 12 separate properties that he identified in that 7-week time frame. So he was extremely thorough in his investigation. Because of this investigation, he did ask his wife to allow him to photograph her hand. He actually thought that he had found a new form of energy initially, and he knew that it had to do with light, so he wanted to image her hand. And on December 22nd of 1895, he produced the first noted radiograph, which was of his wife's left hand. And you can see in this image here, this is her wedding ring on her ring finger of her left hand. And the reason they count this as the first noted x-ray was because he actually submitted this with his first paper on December 28th, 1895. And that paper was titled "On a New Kind of Rays." That was the first of 3 papers that he actually published. And he asked the Medical Society to publish that article in advance because he was scheduled to present to the society on January 23rd. And when they published that article, it was crazy and spread like wildfire, so that during his presentation in January, there was literally standing room only. He had to change the format of his presentation to be answering questions about his discovery because it was just so widespread as to what he had actually done. As far as looking at the overview of how x-rays evolved and how they're used, you can see this photograph is of an early doctor's office, because as soon as he discovered them on November 8th, 1895. So they were not created. He did not invent them. They had always existed. He simply was the first to recognize what this was. So his paper was published in December 1895, and pretty much by January of the following year, 1896, February, people were starting to utilize x-rays in the medical field to image patients. So they would take photographic plates and expose them to x-rays, just like Rankin had done, and that's how they actually created the first radiographs. They would look for things like broken bones, gallstones, what else would they look at? Gunshot, like buckshot, kidney stones. So they used it to find a number of different things. It was used by physicians, and here you can see, which is kind of scary, they actually have the 2 ends, the 2 electrodes of the tube connected to electrical supply, and notice they have it running right over a bucket, which I would assume it's a bucket of liquid. So they have the electrical wires going right up, and then this is the x-ray tube with no covering, no shielding, no nothing. And look how close that is in proximity to the patient. There is literally no room between that x-ray tube and the patient. And this was a cause, they came to find out, of a lot of radiation burns to patients because of the close proximity of the tube and not a lot of distance between the source and the actual exposure to the patient. This we can assume is a physician. Notice he has got his hands on the patient, and we'll assume that he's actually imaging the patient. Those initial images that they took, depending on what they were looking at, when Rankin took this first image of his wife's hand right here, this actually took 15 minutes to make this exposure. The first x-rays typically took anywhere from 20 minutes up to 2 hours. So if they were imaging the chest or the abdomen, the patient would have to lie relatively still for approximately 2 hours to get a decent image. If it was an extremity like a hand or a wrist or something along those lines, then it tended to be down in the 20 to 30-minute range. But again, patients would have to hold still that whole time. They couldn't be moving all over the place. Obviously, they could breathe, but they could not move out of position a great deal. Otherwise, the image would not come out. Not only did this cause radiation burns to the patient, but technologists were also very susceptible to being electrocuted at the setup of the tube in the early days. That equipment was not grounded, it wasn't enclosed in anything, and it absolutely wasn't shielded. X-rays were not harmless as the scientific community initially thought. It actually took 3 years. It wasn't until 1898 that they started to notice that there were harmful, lasting effects from radiation exposure. It's kind of like when you go out in the sun. Radiation burns do not occur immediately after or during the exposure. So a lot of physicians and a lot of people in the medical field didn't associate the fact that the burns were coming from the actual radiation and not to the electrical component of the X-ray tube. Some thought that the X-rays were just a natural part of the sunlight and that the burns were just the form of a sunburn, which in one sense they kind of were, but they went beyond that. Thomas Edison actually brought some attention to the dangers of X-rays. He discontinued his experimenting after he was injured. He had injury to his face, but his assistant, Clarence Daly, continued to experiment with the X-rays, and because of his extensive experimentation, in 1904, he was attributed as the first radiation fatality, meaning his death was completely and solely attributed to radiation exposure. So it took 9 years for the first death to be attributed to radiation exposure. In 3 years, they knew something was not right and that it was causing damage, but it took 9 years until 1904 that he was actually credited or listed as the first radiation fatality. And he, those last few years of his life was miserable. The only way to treat radiation burns at the time was to amputate the part. So realistically, between his experiments, he had his left hand amputated above the wrist. He had 4 fingers of his right hand removed. His left arm was removed above the elbow. And finally, they took his entire right arm off at the shoulder. When he was on the tail end of his life, he couldn't sit, he couldn't stand, he couldn't lie down. He was in complete agony until his death in 1904. So not only was he the first radiation fatality, but a lot of the technologists in the day and physicians suffered unhealing sores and burns to their hands, most likely because of the fact that they had their hands in such close proximity to the X-rays and didn't realize that was a bad thing. But a lot of times they would get unhealing sores on their hands, and they would actually have to wear black gloves to cover that so that patients wouldn't get completely freaked out about the fact that they had these sores, open sores on their hand that would not heal. So when they say amputations and gloved hands, that's where it came from. And typically the technologists, or back then they referred to them as technicians, and radiologists tended to have a lot of these issues. As far as X-rays, people were fascinated with X-rays, and by 1900, so 5 years after their discovery, there was improvement in the imaging plates The equipment had undergone some improvements, and the techniques nearly eliminated acute radiodermatitis. So that's what patients were suffering from in the beginning, was what was called acute radiodermatitis, which was basically radiation burns. Based on the equipment we were using, the image receptors, the techniques that they were using were probably extremely high. And as they studied and learned more about it, they realized that they could improve the equipment in the image receptor and actually lower the technique to, or the dose to the patient. In the medical community, they did recognize many of the early problems with x-rays, and they were doing their best to correct those issues, but the public actually took a fascination with x-rays. X-ray was a term that was used in poems, songs, it was the reference in many plays, and it also appeared in some commercial advertisements for x-ray stove polish, claimed to get your stove cleaner, headache tablets that used the word x-ray claimed to cure your headache quicker. X-ray golf balls had the claim that they would fly farther. There was x-ray prophylactics, batteries, powders, all different kinds of things that just used the term x-ray in it because it was just so fascinating at the time that they would just use it on anything and everything. They would incorporate it into all kinds of products, but realize that all the products on this slide, x-rays had nothing to do with their effectiveness or how efficient they were or how far a golf ball flew. It was simply a way to use the name to bring about more sales. There was one thing though that actually did utilize x-rays, and it ended up proving to be harmful. But when they applied the x-rays to this particular device, this is called a shoe fitting fluoroscope. What this did was allow basically the child would put on shoes that they were going to purchase, and the child would stand on this ledge, hold on to this little railing right here, and the child would bend over and look through the viewfinder. On this side, we had two other ones. One was for the salesperson, one was for the parent, and they would all look through there and see the bones of the foot inside the shoe. And by doing that, they could tell if the shoe was too small, if it was just right, or if it was too big. They would literally look through these viewfinders on the top of the fluoroscope and visualize how the foot sat in the shoe. Now, what's the problem with that? Well, this is radiography in motion because it's fluoroscopy, so it's live imaging. So with little Johnny standing on this step and his feet in there, the downside is that little Johnny's gonads are right about here, which is just in line with the x-ray tube that would be found behind that wooden panel. Okay, so the radiation dose to a child was pretty significant, all in the name of trying to make sure that their shoes fit well or that they had room to grow into them. All right, so not only the radiation dose to the patient, but think about the parents and the salesperson that is doing that multiple days a week. Okay, so it was a legitimate use of x-rays compared to these back here, which did nothing for the product. This actually did work for the product and the consumer. The downside was that the dose was just ridiculous to children, not only males but females. Anyone standing here, that was not a decent amount of dose, or it was not following the ALARA principle. It definitely would have violated the as low as reasonably achievable principle. The book goes on page 5 to discuss some general principles about units of measure. And they talk about the units of measure. We pretty much have the British system and what's called the SI system, or the Système International. A lot of we can call that the metric system. So with regard to units of measure like mass, length, and time, we here tend to use the pound for mass or weight, the foot for length, and second for time. But in the SI system or the metric system, what we're supposed to all do is use the SI system so that no matter where you are or what country you're from or talking to, communicating with, if everyone used the SI system with regard for kilogram for mass, meters for length, and second for time, we could all communicate in the same language. That's ideally what we're supposed to do. But in the United States, I feel like we make everything difficult. So not only do we have the SI system, but we also tend to follow the British system as well. When we talk about these units of measure, not to go heavy into this, but recognize that when they talk about energy, it's simply the ability to do work. And there are two states of energy. There is potential energy and kinetic energy. Okay. Potential energy is the energy that's in a stored state, meaning it has the potential to do the work. But if it's in a stored state, like in a battery, it's not going to work until the battery is placed somewhere where the connection is made. Whereas kinetic energy is energy in motion or expended energy. So it's when it's actually in motion, actually creating the work. Right? And then some different forms of energy. We have electromagnetic energy, which is the one that is most important to us in the radiologic technology field. We have electricity or electrical energy, chemical energy, mechanical energy, and thermal or heat energy. Okay, so we have all different forms of energy, and the most important to us in our field would be the electromagnetic energy. All right, we have some significant radiologic quantities as well that fall into the British system and the SI system. And I would tell you that these quantities are specific to quantify the amount or the dose of radiation based on its effects. All right, so the British system, I will also share with you, is no longer used on the registry. The only thing the registry uses in the form of its questions and or answers is the SI system. All right, so what do these represent? The Rankine in the British system, which is represented by a capital R, the Rankine basically measures exposure in air. I think, yeah. So the Rankine quantifies radiation intensity, or it measures the exposure in the air. And the SI equivalent to the Rankine is a coulomb per kilogram. So these right here are the only ones that the registry is going to ask you about. Okay, we might reference both of them, but as far as the registry, they're only going to talk about how, as far as exposure in air, the coulombs per kilogram. As far as gray, which is the radiation of dose or the dose to a human or an animal, we'll talk about this a little bit more, but it's going to be represented in gray. Sievert is occupational exposure, and a becquerel measures radioactivity. So on the registry, these are the only ones that they will refer to. Now, the coulomb per kilogram, that is a measure of the number of electrons liberated or released by ionization per kilogram of air. Okay? Ionization, by definition, is the gain or the loss of an electron from an otherwise stable atom. What do I mean by that? I mean that typically if it's a stable atom, it has an equal number of protons to the number of electrons, meaning for every positive charge you have in the nucleus, you have a negative charge on the respective shells. They should all add up to the same number of protons. If you ionize something, which is the dangerous or the harmful side of what we do with x-rays, if you were to ionize matter or ionize the patient with the radiation, what that means is that when the radiation comes in, it has the potential to knock out an electron from an orbital shell of a body atom. Now, why would that be significant? Because if that particular body atom is undergoing a mitotic state where it's reproducing and it has a mutated form, it's going to duplicate in that mutated state, which means you basically have cancer at that point. Now, does that always happen? No, it doesn't always happen, but it happens enough that it is a potential. We have to be mindful. That's why we try and follow the ALARA principle, to keep the radiation exposure as low as we possibly can, because what we use is ionizing radiation. Okay, so the British equivalent to the coulombs per kilogram is the Rankine. Okay, and typically when they measure that, they're looking for the output intensity of the equipment or the intensity. And anytime you see the word intensity, you want to think quantity. Okay, so let's look at that. Intensity, I'll try and write this. All right, intensity is quantity. Quantity, like how many, how much, the number of photons. Okay? How many or how much? It's the quantity of photons. So Rankine measures exposure in air, or it references the exposure in air, the intensity, the output intensity of the equipment, or the intensity or the quantity of exposure in air. So the SI unit is the coulomb per kilogram, and the traditional or British unit is the Rankine. The gray is a unit of absorbed dose. Typically, it expresses the amount of radiation that's absorbed by the tissue that's getting radiated. All right, and typically when we talk about the British equivalent to that, it is the RAD, which literally stands for radiation absorbed dose. And that quantifies the effects of radiation on humans and animals. So we have a RAD is the British unit, gray is the SI unit. A sievert measures occupational exposure. Now, who's occupational exposure? That's us. Technologist, radiologist, physicist, not the patient. The patient is measured in a gray. We are measured in sieverts. Technically, we're probably measured more like in millisieverts because we only get 1/1000th of a sievert, typically. The unit specifically addresses the different biological effects of ionizing radiation to which a radiation worker may be exposed. And the standard unit for occupational exposure is the REM. And the REM literally stands for radiation equivalent man. So the REM is the British unit, the sievert is the SI unit. And the last one we talk about, the radiologic quantity, is a becquerel. And the becquerel quantifies or measures radioactivity. right? And it says it's an expression of a quantity or an amount of radioactive material, not the effect of the radiation coming from it. It's just how much radioactive material is there. And the SI equivalent, the British unit that is the equivalent to the becquerel, is a Curie, just like Madame Curie. Curie actually, and let's see, her name was Marie Curie, and her husband Pierre were actually contemporaries. This gentleman's name was Henri Becquerel, and they all were with radioactivity. So Curie got recognized with radioactivity by the British unit, whereas Becquerel became the SI equivalent to that. So if we look back at this chart one more time, again, this is the radiologic quantities, and they are used to measure differing amounts or doses of radiation. So in order, this is the British system. This is the equivalent in the SI system. So the Rankine and the Coulomb per kilogram measure X-ray output intensity, like the amount of radiation coming out of our equipment, or it measures exposure in air. That's both of these. The radiation absorbed dose, or the RAD, is the SI equivalent, is the gray, and that measures absorbed dose like in your patient, in a human, in an animal. If your dog gets an X-ray, they could measure the amount of radiation to that dog in terms of gray. Same thing with if you go to the dentist and get X-rays of your teeth, you would get a certain amount of gray or milligray with regard to exposure. But while you're working and you're doing fluoroscopy on a patient, you would actually get exposure to your occupational self would be in the form of sieverts or millisieverts. And the British equivalent to that is called a REM, which is radiation equivalent man. So this is occupational dose. So if I'm an X-ray tech, my occupational dose is measured by my dosimeter that I typically wear. So when I go to the dentist, even though I'm an X-ray tech, I would not wear that dosimeter, but it's not occupational exposure, meaning I'm not being exposed at work. Going to the dentist would be a personal matter. So you don't measure that with your work dosimeter, okay? And then the last one, which really isn't super significant to us in our field, but would come into play in radiation therapy or nuclear medicine, is the Curie or the Becquerel, which measure radioactivity. So the British system is the Curie, the SI equivalent is called the Becquerel, and those deal with radioactivity. All right, and all of that information literally can be found starting on page 7 all the way through to page 8. And they do give you the mathematical formulas to convert them, but that is not something that we need to be concerned with right now. Eventually, yes, you will have to convert them, but not until further on in the program. All right, so then they kind of move and switch gears, and they jump into radiographic equipment. Oops. Radiographic equipment. And this radiographic equipment is on page 8. Oops. Sorry about that. Okay. All right, on page 8, they talk about that equipment can either be classified as what we call mobile equipment or permanently installed equipment. Okay, so 2 classifications. Now, when it's mobile equipment, Basically, it means that the X-ray unit is typically either on wheels or can be moved from one location to another. You could take it to the patient's bed in a hospital room. You could take the unit to the emergency department and X-ray a patient. You could take, like the C-arm would go into the surgery center, and you could do patient surgery in there or help the surgeon to image the patient during surgery. Anywhere that you can take the equipment to the patient is considered mobile equipment. Permanently installed equipment refers to units that are fixed in place or kept in a particular room designed for X-ray. It doesn't mean that it permanently installed, it can never ever be removed. It just means that, like in our lab, we have 2 rooms with permanently installed equipment, meaning that equipment can't really go anywhere else but in those lab rooms. But if you had a portable machine, that would be considered portable equipment or mobile equipment, because you could take that machine and then move on and go to a patient and get their images. Typically, when we talk about permanently installed equipment, it consists of different pieces of equipment. So permanently installed includes the tube, the collimator, the table, a control panel or a control console, the tube stand, and a wall unit. All right, and all of these things we will discuss, but when they talk about the tube, that's this area right here is the tube. Okay, this is, you can see it says X-ray tube, and there's all kinds of components in here that we will actually discuss and break down. The collimator is this right here, this square-shaped box attached, and what this allows you to do is change the field size. It allows you to collimate or make the field smaller, or you can open up the collimation and make the field size bigger. The table is typically what the patient lays on in order to get the X-ray. The control panel or control console is what we use to actually set the technique and make the exposure. The tube stand is what actually holds the X-ray tube and the collimator in place over the patient, and those have different forms. They can be ceiling mounted or floor mounted, and we'll discuss those in a few minutes. And the wall unit, sometimes we'll call that the chest board or the wall bucky, is another unit where a patient can have their images taken, but typically they're standing up for those images. Okay, and when they reference this right here where you've got the X-ray tube, the collimator, and the tube stand, those make up what is called the tube head assembly. So all of this right here, when you're able to move it back and forth in the room, they tend to refer to that as the tube head assembly. All right. Let's see. As far as the X-ray tube, just to go into this part a little bit more, they don't have everything listed in here that is actually in the tube, but in an X-ray tube, there are 2 electrodes. Remember back in the picture where we had the physician, and I said that these were electrically connected to each of the electrodes. So you have 2 electrodes in the tube, and our tubes today are not that much different from what were used in Rankin's days. They're definitely more efficient, but they still have the same components. So they have 2 electrodes. One has a positive charge, which is called an anode. The other one has a negative charge, which is called a cathode. Okay, and those 2 electrodes convert electrical energy or electricity into X-rays, and they also produce heat as a byproduct. Okay, so we have 2 electrodes in the tube, and their whole purpose is to release electrons and convert that electricity into electromagnetic energy. I'm trying to get back to that slide, sorry. Okay, so within here, this right here, this side is the anode. This side over here is the cathode. So this side is the negative side. This side over here is the positive side. So each of those is an electrode, and two electrodes make a diode. And a diode is something that only allows electron flow in one direction, right? Because when we create X-rays, we also create large amounts of heat as a byproduct, this X-ray tube sits inside this housing, right? And the purpose of this housing is to absorb any radiation that might escape the tube. It also is filled with oil, dielectric oil, to help protect the tube from getting damaged. So while the unit is on and when we're making the exposures and all that heat is generated, the metals in this housing as well as the dielectric oil will help absorb some of that photon energy and definitely absorb some of that heat so that that heat is not escaping. Typically though, the tube housing gets very hot to the touch during an exposure. The collimator, like I said, its main purpose is to adjust the field size or the X-ray, the size of the X-ray field, meaning how much light you see on the patient. All of that area, in theory, will be exposed to radiation. Where there is no light, should not be exposed to radiation. All right, the tube stand or the tube mount is the portion of the tube head assembly that allows mobility of the X-ray tube, meaning that this right here is considered a floor mounted tube stand, and this is ceiling mounted. Now there's much more flexibility in the ceiling mounted tube. This is typically what you will have on clinicals. But this right here is what we have in the lab. Now, is it a bad thing? No. It just means we don't have as much wiggle room with this particular unit as we do with this unit. When the cables are connected at the top like they are here, you have much more room to move the tube and still achieve a diagnostic image. You can go farther with the tube when it's mounted in the ceiling. With this, you're limited by the length of the track. You can only go up and down this far, and you can only go height-wise as far as this will go, which is, you know, that level right there. The difference is likely cost. This is a fixed table height. This one is height adjusting. So this white would literally cover all of the blue, and it would go down probably a little bit further than that. So this is considered a high-low table or a vertically height adjusting table. This is considered a fixed height table. Okay. So floor mounted, ceiling mounted, or overhead mounted would be another way that they could describe that. And the overhead tube mount is the most widely used system in a hospital. Okay, so everywhere you go on clinicals will likely have an overhead tube mount. All right, the table. That was the portion we just looked at. We do sometimes need it to properly position patients for an exam. Sometimes they stand up, sometimes we don't need them to do anything except just stand still, but many of our exams do require a table. Now they're designed to raise and lower, which we call height adjusting or vertical adjusting tables. Typically it'll have a four-way float on the top with an electromagnetic lock, meaning when you step on a foot pedal, in this picture back here, right here is the foot pedal for table A, and then on this one, it's probably this gray right here. which is your foot would actually go in there a little ways and step down on that. But that is considered a four-way float. When you step on those, it allows the table to move up and down and side to side all at the same time. Okay. They also talk that there is a variation when we use fluoroscopy equipment. Typically, the table used in fluoro will have what they call a 90-30 tilt or a 90-degree, 30-degree float. And what that means is the table would go 90 degrees upright so that you could start the patient in an upright position. And the 30-degree Trendelenburg means that if the patient started to pass out or feel really lightheaded or really sick to their stomach, you can actually lay the table down when you're doing fluoro and allow them to feel a little bit better. The wall unit. There is no picture in the book of a wall unit, but this literally is a unit that sits on the wall that is adjustable, and this is done for any upright images that we need to take. It does allow for height adjustment, so if your patient is shorter, then you can move it down. If they're taller, you can raise it up, and it's just exactly the same as the table bucket. There is a tray in the table that holds the image receptor. It's the same exact thing that we would have in the table, except that it mounts to the wall. And again, that's to get or obtain any upright images. The control panel is the last portion, and this is where we set our technique. We set our parameters of what we're going to use to make the exposure. So we select our kilovoltage, we select our milliamperage, and by selecting our kilovoltage and milliamperage and our time, that will end up telling you what will be applied to the X-ray tube in order to produce X-rays. And the control panel allows us to fine-tune or modify the exposure to best image the area that we are trying to image. Okay, so we select our kilovoltage and our milliamperage. That's not probably the only thing we select. We also would select the anatomic programming for what we're going to image, the focal spot, so that we get the most amount of resolution in our image. And we possibly could use what's called the automatic exposure control, which we will talk about more in depth. As far as fundamentals of radiation protection, we do always want to follow the ALARA principle, and we've said many times before that that stands for as low as reasonably achievable, meaning that we are bound by our organization and our profession that we are responsible to keep the radiation dose not only to our patient and to ourselves, but to any others as low as possible, as low as reasonably achievable. Meaning, if you don't need someone in the room, ask them to step out. If you don't want to radiate excessive people, ask them to move back or step out of the room, because it's on you to adhere to that policy. And it's not just a policy. I mean, it's literally our, it's huge in our field. You just always want to act in the best interest of the patient and adhere to that ALARA principle at all times. The ASRT and the ARRT also support the fundamental of radiation protection, and it is actually a violation of the Code of Ethics, and in a lot of states, a violation of the state license law if you don't keep the radiation dose as low as reasonably achievable. Okay? That's how strongly they feel about that. The ASRT, the ARRT in several states enacted legislature that if you violate the ALARA principle, you can absolutely be brought up on a professional ethical violation. All right. As far as minimizing radiation dose to the patient, these three things here, shielding, time, and distance, we consider these are cardinal rules of radiation protection. And I can tell you that they apply to not only us, but to the patient as well. When we talk about shielding, that typically refers to using radiopaque materials like lead to reduce the radiation exposure to parts of the patient that are not needed to be imaged. So we can use a lead shield over the patient or over ourselves if we do not want a specific area exposed to radiation, or we're trying to limit the areas of exposure. So not only can we shield the patient, but we've also talked about how we can wear shielding as well when appropriate to protect ourselves. If we have to be in the room, we should be wearing lead shielding, like during fluoroscopy. As far as time, it is the duration of the exposure to the ionizing radiation. So as far as a patient, it could be the exposure time for the exam that we always want to minimize. And if it's with regard to us, we don't want to be in the room more than we have to be. So if we're able to not be in the room when the patient is being done, we have that right to step out. Distance is the space between the patient or ourselves and the source of ionizing radiation. So the reason that that's important is because of the inverse square law, which simply states that the intensity or the quantity of radiation diminishes over an increased distance, meaning the farther away something is from the radiation source, the radiation is actually going to spread out in a wider area and potentially dissipate. So if you can put more distance between yourself and the X-ray tube, that is always a good thing. Patients are kind of limited because we have to utilize the appropriate SID, but assuming you're using the appropriate SID, that's protecting the patient. As far as us, if we can take one step back during fluoroscopy, we absolutely should do that. If you can stand behind the radiologist during fluoroscopy, should absolutely do that. So again, these are the cardinal rules of radiation protection, and they are your time, distance, and shielding. Okay, I will tell you with regard to shielding now, the AAPM, the AACR, or I'm sorry, the ACR, AAPM, and other organizations have proposed new training of technologists and technologist students. We are going to start eliminating shielding for patients. They feel that it is actually doing more harm than good, and especially with the introduction of digital imaging, that exposure to the patient is so low as it is, that by having the patients wear those lead shields, that it actually is trapping the radiation inside the patient versus allowing it to get out and leave the patient. But as far as the registry is concerned, we still do teach shielding. I don't want you to think that it's okay to just, whatever, and not shield, but it's according to your site's protocol. If they still follow shielding practices, then we have to follow shielding practices. All right. Some of the tools that are used in radiation protection is to limit the field of X-ray exposure, which basically means that you collimate or you restrict the beam. Okay, you never want to radiate any area larger than you have to. You always want to keep the area of interaction small if possible. We also are able to control the settings on the control panel, and we typically always want to use the highest possible KVP because that represents the beam's penetrating ability, and we always want to use the highest KVP and the lowest possible mass value. KVP does control the penetrating power of the beam, and mass controls the quantity of photons in the beam. So you always want to try and use the most penetrating beam that you can so that the radiation doesn't actually stay in the patient but exits the patient. You always want to avoid any unnecessary repeating of exams. Will we make mistakes? Yes, we are human, but if you can avoid any unnecessary repeats of exposure, then by all means you want to do that. Always screen patients for pregnancy. If possible, we want to minimize our radiation dose to a fetus. So you always want to ask female patients if there is any chance they could be pregnant. And sometimes they have to actually sign that they're not, or to the best of their knowledge, they're not. So that is something else that might come into play as far as radiation protection, having those forms signed. And last, get it right the first time, meaning go slow enough and be methodical enough that you actually get the image correct the first time. Better to take a few more minutes and get it right than to rush through it and find out that you had done something wrong and that you have to repeat it. Because when you repeat, you don't erase the initial radiation that you gave to the patient. You're simply adding to that amount. So just because you're taking another image and starting over, it doesn't negate what you already gave to the patient. So you always want to make sure that you give them the least amount possible, and you always want to attempt to get the most diagnostic image possible. The last part of that chapter is very important, and I know they go into much more detail than we did on that last little slide. So make sure that you look over this. Some of the stuff, again, probably very repetitive and you already knew, but a lot of that stuff is brand new and you did not know it. So once you are done with this lecture, I hope that you printed out the slides. If you had anything that was confusing or you did not comprehend, or you just want to hear it one more time to make sure that you got everything down the right way, then make sure you write those down and we will discuss them at our next live. And until then, I hope you guys have a great day. Thank you.